This problem is very similar to problem number 4 on the homework for section 4.5. Your numbers will be different, but the process will be very much similar. We have a species of bird that's in danger of going extinct. The population is decreasing exponentially. We have a population 8 years ago, the population now, and we have the point of no return. Once the population gets below 300, we won't be able to save this species of birds and they'll go extinct. We want to know how long do we have to figure out what to do about it. When will this happen? Here's our exponential model. A equals A0 times e to the kt. Formulas like this are kind of fill in the blank style, so we just need to figure out what goes in what spot. So reading through, I'm going to notice 8 years. Well, that sounds like a length of time. So when we go to fill things in, 8 years is going to go where t is for time. The population was at 1500. Well, that's the earliest data that I have. So 1500 at the beginning, that's going to be my A0. And I know that there are 900 birds now, 8 years later. Well, that's going to stand in for A. At this point, I know E is a constant. We have a value for everything except for K. K is a constant that describes how fast the population is growing or decaying. If I know everything but K, I can fill all of that in and find a value for K. Let's do that. See, we said A is 900. We have 900 birds now, equals A0. The initial population was 1500 at the beginning when we started measuring. And E to the, I don't know what K is, so we'll just keep calling that K. And T time is 8 years. There's our exponential model for what's going on. When I find a value for K, I'm going to expect it to turn out negative because the population is decreasing. This is exponential decay. Exponential decay, the constant is negative. Exponential growth, it's positive. So I'm expecting a negative value for K. Once we get to here, it's just like solving, because it is, solving an exponential equation. Next thing I'm going to need to do is divide both sides by this 1500 to get the exponential term by itself. 900 divided by 1500 is 0.6 equals, and I have e to the, I have to do 8k. I just feel backwards putting the k in front. I feel better now. Next thing, as we've seen before, the thing I'm trying to solve for is in the exponent, so I'm going to need to use the inverse of an exponential function, which is a logarithmic function, to get it down from up there. I'm going to choose a natural log base e because I have the e in there. So on the left, natural log of 0.6, and then natural log of e to the 8 times k. Well, now we can use a rule of exponents that says when I have the log of something to a power, I can bring that power down in front and multiply. On the left, still natural log of 0.6 equals, and now I'm going to have 8k times the natural log of e. But the natural log of e, that's log base e of e. That's just 1, so I'm not going to write natural log of e, because it's just 1. Actually, once we get to here, we almost have found k. Last thing left to do is divide by 8. So I have natural log of 0.6 divided by 8, which you can do on a calculator. That's k. And I did this earlier, negative 0.063853. Hopefully that's what I said. In order for the solution to be as accurate as possible, yes, you really do need 6 decimal places for k. 1 or 2 is not enough. It won't get the answer accurately enough. Okay, well, great. Now I have a value for k, but we haven't really answered the question yet. So I'm going to come back up here and look at what else we know. We know that once the population goes below 300, that's a bad thing. Well, that's the ending population, like 900 was before. I'm going to start from my exponential model again and fill in again what we know. So this time 300 is going to play the role of A. The initial population is still 1,500. That's the initial at the very beginning, so that doesn't change. And then I'm going to have e to the, well, this time I know k, negative 0.06853. There's k. The question I'm trying to answer now is when. Well, when is a short way of saying at what time. So this time I'm looking for time, and once I find a value for t, this time I'll be done. I do not want to have to type that again, so I'm going to copy it so I can paste it later. The process we're going to use is really the same process we used up here the last time. We're just solving for t this time instead of k. Next thing I'm going to do, I'm going to divide by 1,500 on both sides. 300 divided by 1,500 is 0.2 equals, and I'll just have the exponential part, and I'm so glad I copied and pasted. Now, just like we did up here, we're going to take a natural log on both sides of this equation. So on the left, that's natural log of 0.2. On the right, natural log of that lovely natural exponential expression. Just like last time, I have the log of something to a power. That power is going to come down in the front and multiply, and the natural log of e is 1. So next, natural log of 0.2 equals, I'm just going to end up with what was up in the exponent before, and I don't think I can get out of typing it again, negative 0.063853 times t. Now all that's left to do is divide. I'm going to divide both sides by that value of k, and that'll give me a value for t, which you would do this on your calculator, and again, I did this before, so it's about 25.1. We're measuring time in years. This says we have about 25 years to figure out what we're going to do for this population of birds so that it doesn't go extinct.